In this slidecast, we'll discuss quicksort. Quicksort was developed in 1962. It selects a specific value called a pivot and then rearranges the array into two parts. This is called partitioning. And all the elements in the left subarray are less than or equal to the pivot, and all the elements in the right subarray are larger than the pivot. The pivot is placed between the two subarrays, and this process is repeated until the array is sorted. Okay, here's an example to show how this works. We arbitrarily select the first element as the pivot, and then we swap the pivot with the element in the middle. Now we partition the elements so that all the values less than or equal to the pivot are to the left, all the values greater than the pivot are to the right. And that just happened. We'll go into more details here in a moment. But the gray values are less than 44. The pink values are greater than 44. So 44 is now in its correct position in terms of the final sorted array. So we repeat this process recursively, okay, on the two subarrays. So now we choose a pivot of 12, and we sort the subarray. In this case, 12 was the smallest value. Then we choose 33 as the pivot. We place it in the middle and sort. So now 33 is in its correct position. And the left and right subarrays have a single value, so they're considered sorted. Now if we go back to the upper half of the array, 55 is the pivot. It was the smallest value. If 64 is the pivot, it's also the smallest value. If we choose 77 as a pivot, we've got to swap these. And now that there's only size 1 subarray, it is considered sorted. So now the full array is sorted. Now, we describe how to do the partitioning later, but if the iterators first and last are the end pointers of the array being sorted, then pivot is a pointer to the pivot value after partitioning. So here's the algorithm for quicksort. If the sequence has more than one element, partition the elements in the iterator range first through last so that the pivot value is in its correct place and pointed to by pivot. Then we recursively apply quicksort to the sequence in the iterator range first through pivot, and we recursively apply quicksort in the iterator pivot plus 1 through last. Now if the pivot value is a random value selected from the sequence, then statistically half of the items would be less than the pivot and half would be greater. And if both subarrays have the same number of elements, there will be log-n levels of recursion. So at each recursion level, the partitioning process involves moving an element to its correct position, so there's n moves. So quicksort is an order n log n algorithm, just like merge sort. Now the array split may not be the best case. It might not be split in half. So an exact analysis is difficult, but the running time will be bounded by a constant times n log n. Now quicksort will give very poor behavior if every time the array is partitioned, a subarray is empty. So in that case, it would be order n squared. So under these circumstances, the overhead of recursive calls and the extra runtime stack storage required by those calls makes this version of quicksort a poor performer relative to the quadratic sorts. And we'll discuss a solution to this in a bit. Here's some code for quicksort. Got our quicksort routine. We do our partitioning, sort the left half, and we sort the right half. So here's an algorithm for partitioning. If the array is randomly ordered, it doesn't matter which element is the pivot. So we pick the first element. In this case, 44. Now for visualization purposes, items less than or equal to the pivot will be colored blue. Items greater will be colored a light purple. So again, the blue items are less than 44. The purple items are greater than 44. So we search for the first value at the left end of the array that's greater than the pivot value. So that's 75. And then search for the first value at the right end of the array that's less than or equal to the pivot value. And then we'll exchange these values. and then we just repeat that. So 55 is the first value that's greater than the pivot. 12 is the first value coming down from the right that's less than the pivot. We'll swap these two, and we just keep repeating that until we find the first element at the left end is greater than the pivot. So now we're done. So the first element at the right end that's less than or equal to the pivot will go, since down has passed up, we don't exchange, and we exchange the pivot value with the value at down. So we'll swap 44 and 12, and that lets 44 is now in its correct position. So here's the pseudocode for this partition function that's listed here. We define the pivot value. We initialize up to first plus 1 and down to last minus 1. And here's where we're incrementing up to select the first element that's greater than the pivot, and kind of the opposite thing as we decrement down until it selects the first element that's less than or equal to the pivot. And if up is less than down, then we can exchange those two values. And we just keep doing that until up is to the left of down. Then we exchange table sub first with table sub down and return the value of down to the pivot. Here's an algorithm for partition function. If we set up first and last, we have 30 be the pivot, and down points to the first one, up points to the very last. Now if we choose 85 as our pivot, in this case, then up and down are pointing to 50, and after the swap, we'll swap 85 with 50. Here's the code for partitioning. I encourage you to stop and study this, here online, or go to your book. Quicksort is order n squared when every split yields one empty subarray, which is the case when the array is pre-sorted. Now the worst possible performance occurs for a sorted array, which is not very desirable, so a better solution is to pick the pivot value in a way that's less likely to lead to a bad split. So here's a revised way for choosing the pivot. We'll first look at first, middle, and last, and we'll select the median of these three items. Okay, so here's another revision. We first sort table first, middle, and table sub last minus 1, and we move the median value to the first position by exchanging table first and table middle. And we'll initialize up to first plus 1 and down to last minus 1. And here's the loop where we're incrementing up and we're decrementing down and continuing to exchange them until up and down sort of pass each other. And finally we'll exchange table sub first and table sub down and return the value of down to pivot. So here's our revised partitioning. We start out by looking at considering three values. The middle value is 44. So as we sort that, they're in sorted order. So we'll exchange middle with first, and then we can run the partition algorithm using the first element as the pivot. So in this case, we consider three values and choose the median, and that just helps us avoid extreme cases where we choose a very low or very high element that doesn't partition well. So here's the revised partition function, where we look at the values at three locations, and we move the median value to the first position by exchanging it with table sub first. We initialize up and down, and we go ahead and do our adjustments around the partition value. Here's some C++ code to do this. And here we partition the table so that values in the iterator range first through pivot are less than or equal to the values in the iter range pivot plus 1. Now the pivot value is the median of the first, middle, and last. Here we'll just use bubble sort to sort those middle values. Again, I encourage you to stop the slidecast or go to your book and study these code samples. I'm not going to walk you line by line through them on the slidecast. Bring your questions to class. This brings us to the end of this slidecast.